Hello, my name is Saida. I'm a data scientist at SI. Today I'm going to cover Gaussian mixture models and the expectation maximization algorithm. Let's first recap how k-means clustering works. First, we initialize cluster centers, then assign all the samples to the closest center, after which we update the cluster centers. We keep repeating the steps of assigning and updating until we reach the convergence. However, there are some limitations to k-means. First, what if the clusters are overlapping? Because k-means makes hard assignments, each sample assigned only to one closest cluster. But what about those points that might belong to multiple clusters? Next, k-means uses Euclidean distance and therefore cannot model other shapes, such as an ellipsoid-shaped data. The generalization of k-means that can answer previously mentioned questions is a Gaussian mixture model. The Gaussian mixture model is a probabilistic model that assumes that all data points are generated from a mixture of Gaussians. Let's recap Gaussian distribution. In the case of a single dimension, let's say x is a real-valued random variable. If a probability distribution of x is a Gaussian with mean mu and variance sigma squared, then we can write it as x is distributed as Gaussian distribution and parameterized by two parameters, mean and variance. If we want to plot the Gaussian distribution, it will look like a bell-shaped curve with mean at mu and one standard deviation defined with. This specifies the probability of x taking on different values, defined by the following probability density function. Now, suppose x is a vector. Then we will have a multivariate Gaussian distribution with mean vector mu and covariant matrix sigma. So instead of associating the data with the cluster centers, as done in k-means, Gaussian mixture models the data by learning the distribution for each component. Consider one-dimensional data, where we would like to learn the distribution of two Gaussian components. So with Gaussian mixture models, given unlabeled data, we can learn the mean and the variance of each component. Let's say we will learn distributions as plotted on the graph. Learning the distribution means that we will find the optimal values of mean and the variance of each component. Next, unlike in k-means, GMM assigns data to a component with certain probability, also called the soft clustering. Suppose there is a data point equal to 0. It can be expressed in terms of components of equal importance. In its core, GMM is a linear superposition of Gaussians in the following form, where k is a number of Gaussians. They are also called the mixture components. And mu and sigma are the mean and covariance of each component. In order to understand mean and covariance, let's consider a component in 2D. Here, mean centers the distribution. Next, let's consider the covariance matrix. Covariance matrix specifies the spread and the orientation of the distribution, where the main diagonal elements are the variance terms for each dimension, and off-diagonal elements specify the orientation of the ellipse. Finally, in the PDF of Gaussian mixture models, the omega variable is mixture weights, or priors, which represent how much each component contributes to the final distribution, with the constraint that the sum of all mixture weights is equal to 0. With Gaussian mixture models, we want to learn the parameters of each component given the unlabeled data only. This is where expectation maximization algorithm comes. Given Gaussian mixture model, the goal is to maximize the likelihood of the data with respect to the model parameters. The first step of the algorithm is to initialize parameters mu, sigma, and omega for each cluster. One option is to have a random initialization of the parameters, and the other option is to initialize the parameters based on the results of trained k-means. The second step is expectation step. Given the current parameter values, evaluate the responsibility factor R for each data instance in each component. This factor represents the probability that the data instance xi is generated by the component ck. The third step is the maximization step. Using the responsibility factor calculated before, we will re-estimate parameters omega, mu, and sigma for each component. After updating parameters, we will evaluate the log likelihood of the data x given our new parameters. We want to find parameters so that the resulting distribution matches the data x as much as possible. We will repeat steps 2 to 4 until convergence. If parameters mu, sigma, and omega are learned, the number of components k needs to be chosen before running the EM algorithm. The question is how to select the optimal number k. One way is to perform cross-validation with different number of components and select k based on the validation set results, as measured by the likelihood in step 4. Another common technique is to calculate Bayesian information criterion, which gives an estimation of how good GMM is in predicting the data. In this formula, L is a likelihood value and N is dataset size. The right side term can be understood as adding a penalty for the number of parameters to the log likelihood. So the intuition is to pick the simplest model that will fit the data. The approach is to try different k values and select the one having the highest Bayesian information criterion value. Let's see an example of the EM algorithm. Consider a two-dimensional dataset of 400 points, and let's have a number of components equal to 3. As we start running the expectation maximization algorithm, we can see how the contours of 3 components keep changing until no more changes occur, which is a point of convergence. Finally, let's talk about some applications of Gaussian mixture models. As illustrated in example before, we can use GMM for clustering. The probability that a data instance belongs to a component can be calculated using the estimated parameters. We can choose a component with the highest probability to predict a cluster for a new data instance. Another useful application is data generation. Similar to how sampling from a Gaussian distribution is possible, it can be done using Gaussian mixture models to create synthetic datasets. To do so, we first sample from which component to generate the data. The probability of sampling the component is given by its omega parameter. It can be interpreted as, without observing a variable, what is the probability it is coming from a component ck. Finally, once a component was chosen, we sample data from the selected component given its distribution, which is defined by the learned parameter